So last time I introduced this distinction with, I think, the same color coding. I introduced this distinction between syntax, semantics, and what I'm now calling formalism. I think that's a better catch-all term. So syntax is when I introduce only grammar, when I'm introducing a new symbol, and I'm not really giving you any meaning. Semantics is when I'm introducing the meaning, and only the meaning, but I'm not giving you any deductive tools. I'm just telling you what people are intending for a symbol to mean when they go to make up the formalism. And then the actual formalism provides the deductive tools. That's what we use for proofs, and that includes axioms and definitions. So here are two symbols that we introduced last time, the membership symbol and the set collector notation, or the set builder notation. The membership symbol, we gave this grammar for. Put a term, membership symbol in between, you get a proposition. And it has this meaning. These symbols mean X is an element of A, or X is in A. And then for the set builder notation, you put some curly braces, a bar, a variable there, and a proposition there. And then if you do that, where phi, say, is the proposition, then that means, well, it's a term, and it refers to the set of X such that phi is true. Okay, so that's syntax and semantics, but where's the formalism? Actually, the formalism is going to come all at once for both of these in the same axiom, and that's axiom 5. So here's how that goes. So an axiom, a theorem, a definition, they're all going to be propositions. So I'm going to write down a proposition. And it works like this. A is in. Now notice that this A here that I'm putting in is a variable, and it's showing up, and there's no quantifier or anything like that on it. It's a free variable, so that means you're allowed to replace it by anything when you actually apply this axiom in a particular situation. So that was derived rule 31. Okay, so axiom 5. A is in the set of X such that phi is true if and only if phi holds if you were to replace all the X's by A. So that's the axiom. And let me just show you a quick example. This axiom you can think of as sort of defining the way this symbol works and the way this notation works. So it's defining them each in terms of the other, kind of. Okay, and here's an example using a nonsense proposition. Let's say A is in the set of X such that X is green if and only if. So how would you read this term here without referring to the bound variable X? You would describe this as the set of all green things, right? It's the set of all green things. What does it mean for A to be in the set of all green things? Well, according to axiom 5, it means the phi, the proposition here, holds if I were to take it and replace all the X's by A's. So what do I get when I take this and I replace all the X's by A's? So take this and then replace all the X's by A's. I get A is green. And hopefully that feels right to say that A is in the set of all green things if and only if A is green. So this is an application of axiom 5. This is one instance of axiom 5. Every time you apply axiom 5, it'll be to a specific choice of proposition here and specific choice of variables showing up there and there. There's one, so hopefully this is intuitive that it would work this way. Actually, there's something wrong with this axiom. This is actually broken. And it is broken in the worst possible way. So this allows you to prove a contradiction. If you take this axiom at its full strength, allowing yourself to put any proposition that can be possibly stated here for phi, then you can use this axiom to prove a contradiction. And people ran into this problem in the history of the development of set theory. And it was quite problematic. So for a while, after set theory with axioms not so different from what you're seeing was introduced, people were using it to prove all kinds of things. And one day, someone proved something that directly contradicted what someone else had proven. And you've seen how big of a disaster that is, right? When someone proves a contradiction, the entire system is broken. So this led to total disaster. Some people giving up on math, some people thinking, okay, it's actually hopeless to try to come up with a formalism that captures all of the kinds of deductions we want to make in mathematics. But eventually it was fixed. It was repaired, and it's not so simple to repair it, but there are different ways of doing it. They involve fixing this axiom, or changing the way the notation works a little bit, and making it a little bit more complicated, and then also introducing a whole bunch of new axioms to get certain things to work. Each different way of fixing this broken axiom gets its own name. So, for example, you've got Zermelo-Frankel set theory, or ZF set theory, which is a pretty standard one, which refers to a set theory similar to the one we're doing, except with this axiom fixed in a particular way, and new axioms introduced to make things still work. Another one is von Neumann-Gödel-Bernays set theory, and that's another pretty standard one. And that just refers to another way to fix this axiom and introduce new axioms that make everything still work. A third option that's available to us, which is the option that we are taking, is called naive set theory. And that means don't even fix the problem, just ignore it. And that's what we're doing. So it's naive in the sense that we are allowing ourselves to be naive like those mathematicians who were working in the early days of set theory, thinking that things were really just this simple to get them to work. So our strategy is to ignore the problem. We accept that there are some choices of phi, some choices of proposition here, where if you put them here, then you will be able to use this axiom to get a contradiction. And so we just include this warning. You can think of this warning as saying, don't apply this to bad propositions. There are some propositions we should avoid. So that's really unsatisfying, and it should be fixed at some point. But for the sake of learning this stuff, it's kind of easier to just ignore the problem at the beginning. And then once you gain some familiarity with set theory, you can go back and look at how to tweak things to fix the problem.